Alright, I've been looking forward to this video because we are going to use everything we've learned about SN1 and SN2 and try to apply that to reactions to decide whether a substitution is going via an SN1 or an SN2 mechanism. So today we're going to do a lot of practice problems and summarize, maybe so we could use it as a study sheet, the differences between SN1 and SN2. Before we get to that SN1 versus SN2 table, let me show you an example of how I would analyze a reaction to decide whether a reaction undergoes an SN1 or SN2 mechanism. And let me put directions also. So, example. We're only going to worry about substitution reactions in this video. Draw the substitution product or products. Okay, we might have a racemic mixture for each. My abbreviation for reaction is RxN. I'm going to put here a little disclaimer. Do not worry about potential elimination processes, or not worry about competing elimination reactions. I'm going to go over elimination reactions in the next unit, Unit 8. Alright, let's start out with this. Alkyl halide. Go ahead and copy this. I'm taking this from a textbook, and this is exactly how the textbook writes it. I wouldn't normally write it like this. I would write maybe the reagent and the solvent over the arrow. Your reactions on an exam are not going to be very clean. It may not be very obvious at first what is the nucleophile, what is the solvent. Okay, because take a look at this combination here. How do we decide which one's the nucleophile and which one's the solvent? Well, whenever you have water with something else, you are going to assume that water is the solvent. Okay, it's not. They wouldn't. I don't imagine they would ever dissolve a little bit of water in methanol and hoping that water is the nucleophile. You would dissolve a little bit of methanol into water and have methanol the nucleophile. Okay. So this is your analysis, or my analysis. I'm going to draw some lone pairs, but I'm going to decide now that this is a nucleophile. I'm going to decide now that this is a solvent. What do I know about the nucleophile? It's a neutral nucleophile, so I'm going to say it's poor. Okay. The solvent is polar protic. What am I headed towards, do you think? If it's a poor nucleophile, typically it's not going to kick out the leaving group very easily. It's not a very strong nucleophile. So instead of kicking it out, the nucleophile is going to wait until the carbocation is formed. Okay. If you take a look at our cartoon, that's this process up here. See, the cat is waiting until the leaving group leaves. Here, the nucleophile is strong and it pushes out the leaving group. So we're expecting this. This is SN1 on top. Alright, so I am going a little bit quicker because this is the speed at which you want to analyze your reactions on an exam. If you're a little bit unsure of yourself, go ahead and rewind. Look at the previous videos. I think there were at least 4 of them before this video here. Okay. Polar protic. When we talked about solvent effects, didn't we say that polar protic solvents favor SN1? So far, the solvent, the nucleophile, are saying SN1, which is good because My alkyl halide is secondary, and that is on the fence. It's not very crowded, okay, but it's also not very uncrowded. If we do SN1, we'll have a secondary carbocation, and that's not the most stable, but a secondary carbocation is also not the least stable. So this is on the fence. Okay, but because of your other determinants, we're going to say it's SN1. What do we know about SN1? We know about SN1 is that it goes through carbocation. And we should always think about the geometry of carbocation. It's flat. So this nucleophile there can come in front or back. That's your product. Front and back. You get both. It's not or, it's and. You get this and this, 50-50. This is racemic. What do I expect on the exam? The grader is looking for this. In this case, two products, and they are racemic. The grader is making sure that there's no hydrogen here. Remember, when the nucleophile attacks, if it's a neutral nucleophile, almost always you'll have to remove that hydrogen in the last step to make it neutral. Okay, so we got rid of this hydrogen here, and we use only the methoxide as the added group. Okay, I'm not going to go through mechanisms in this video. What I'm more concerned about is, can you do everything in green? So while the grader is looking at the blue, the two products and racemic, what do I think that the people who are getting A's in class, what are they doing? They're doing everything in green. They're identifying the nucleophile. They drew the lone pairs because this is the attacker, right? This oxygen's the attacker. A common mistake is that a lot of people do realize that this is a nucleophile, but they put the point of attachment on the carbon. No. It's this carbon dot connected to the oxygen, the atom that was attacking. Okay? So you may think it's extra work, but no. All of this green writing is to help you prevent any careless errors. Okay? And most of the students who do well are putting down, well, what does this represent? If it's a poor nucleophile, it's a vote for SN1. If it's polar protic, it's a vote for SN1. If it's secondary, I'm not sure if it's SN1 or SN2. Okay? So SN1 wins. That's the process. Now, if you don't understand why a poor nucleophile gives SN1, or why a polar protic solvent gives SN1, that comes from the table. In the previous video, 07 F20, let me write this down. In a previous video, 07 F20, we have our cheat sheet. We have our table, or we have our cheat table. Okay. If this was open notes on an exam, I would have this written out. And what is that? It's this right here. Okay. Take a look at what we have in the reaction. Take a look at our table. Poor nucleophile. That is not on the table. We could add that later. Oh, maybe this one. See, the nucleophile weights. So that implies that this is a poor nucleophile. SN1. Good. So we have that. Polar protic solvent. Polar protic solvent. Right there. SN1. Okay. Secondary alkyl halide. SN2 if it's primary. SN1 if it's tertiary. Secondary is on the fence. Okay. What about this? The idea that we have a mixture that we took something that's chiral and we scrambled it. We made R and S. Right there. Scrambling. Not inversion. You have scrambling. You see how this table, if you can memorize this, okay, but also there's rationale for each of these points. But if you can memorize this table, you'll avoid any careless errors. Okay. So I'm not going to reproduce that table. You have it in video 07F20. I'm just going to keep going. Let's take a look at our next problem. We'll call this problem A. Problem A. Let's look at problem B. Problem B, the alkyl halide is not chiral because we have no chiral carbons. I'm going to draw the reagent over the arrow, and I'm going to give us a solvent. I'm going to ask you to pause the video in just a second. When the video is paused, I want you to draw the nucleophile with the lone pair and the possible charge. I want you to figure out whether DMSO, looking through your notes, is polar protic or polar aprotic. And I want you to label if this is primary, secondary, or tertiary. Based on what you have in green, could you decide whether you're going to do an SN1 process or an SN2 process? Okay. All right. Again, label each of these things, figure out whether you're SN1 or SN2. Okay, go ahead and pause the video. Okay. The nucleophile typically trips people up for some reason because a lot of times it's not drawn in the form in which it attacks. The NaCN, really what you want to visualize is this. See, there's your attacker. There's your nucleophile. And what kind of nucleophile? It's a good nucleophile. It's anionic. That suggests that we're likely to do SN2. Take a look at the solvent. This is polar. And from a previous video, we listed all the polar aprotic solvents that you want to know. SN2. So far, everyone's in agreement. Put a dot on this molecule here. This is considered what's called the alpha carbon, but it's the carbon connected to the halide. This carbon is connected to one other carbon. This is primary. Very uncrowded. SN2. Fantastic. Now, SN2 implies that you have inversion, that there is backside attack. But even though that happens, you don't see it if you don't have a chiral carbon, because when you draw the product, there's no way to know whether it was backside or frontside attack, because there's no chirality, there's no reference, there's no RNS. Because, for instance, if you have an R alkyl halide and you do backside attack, mainly, not all the times, but mostly, you're going to go from R to S, and vice versa, you could go from S to R. But if you have no RNS here, you shouldn't have any RNS on your final product. And you could draw the final product like this. Okay. So we added a carbon, right? The carbon from the cyanide. So here we have 4 carbons. 1, 2, 3, 4, and here we have 5. 1, 2, 3, 4. And this carbon here of the nitrile group, or the cyanide. So that's the N. You could call it a cyanide group or a nitrile group. This specifically is called the cyanide nucleophile. Alright? So maybe also the professor will ask, okay, you drew a good substitution product, but is it SN1 or SN2? They want it stated. So for me, sometimes I'll have a box, and you have to tell me if it's SN1 or SN2. The thing is, whether it's SN1 or SN2, the product looks the same. That's why I want to make sure that you know it's SN2. Because if you had thought this was SN1, you would get the same product. Okay. For this one, the first one we did, this was SN1 and we got scrambling. Okay, SN1. If it was SN2, then we would get inversion. We would only have the dash because we started out as a wedge for the halide. Do you see the strategy? Let me zoom out a little bit and you can take a look at these two problems, A and B. Okay. There is a lot of legwork. There's a lot of work up front in green to make sure that your answer in blue is correct. Let's try one more. Well, we're going to try a lot more because we do have almost 15 minutes left. Let's do C. Okay. I am going to draw the starter material, the reagents, and the solvent. You're going to do all your analysis in green, and you're going to put your answer in blue. Okay. So all I'm doing is drawing stuff in black, and I'm going to ask you to pause the video. Let's do this one. And let's do that. Plus, I'm putting these problems in a lot of different forms. Sometimes the reagents next to the starter material, sometimes it's over the arrow. There'll be times where I give the solvent, times where I don't. If I don't give the solvent, then you can't assume anything. Okay, you don't have a solvent to make a decision on. So you have to decide based on the other components of the reaction if there is no solvent. In this case, how about, okay, this might be a little bit trickier to analyze, but this is definitely valid. And then I'll just put here acetone. I want the product and I want the mechanism. It's either SN1 or SN2. If you really want to do well on the exam, then you would also write your notes. I write my notes in green. Okay. Alright, you're going to pause this. I expect maybe this will take between 3 and 6 minutes, okay, depending on how far you are in your studies. Please pause the video, and when we come back, I'll show you the answer. Okay, if I get this problem on the exam, I want to try to do this in a very time-efficient manner. Okay, and I'm not going to say anything. Okay, that's my answer. The asterisk is not necessary, but if you're confident that that's the carbon and you want to mark it, go ahead and mark it. I'm showing you that it goes through inversion because I think the mechanism is SN2. I think it's SN2 because polar A products favor the SN2 pathway. A good nucleophile, the cat doesn't wait. The orange cat attacks to kick out the leaving group. That's SN2. You need the orange cat and the gray cat in the what's called the rate determined step. Okay. Now that we have 3 examples, what can you do to practice? You can just recopy them, and again, obviously without the answers. You're going to ask yourself, can I draw the mechanism? Again, we're not doing the mechanisms in this video. I want to make sure that people can predict the product accurately, predict the substitution product. just recall that probably in a week, for a lot of you who are taking this in the fall or spring, in about a week, you're gonna look at these with a different perspective, because in a week you're gonna learn elimination reactions, which is a competing reaction. But for now, we're only worried about substitutions, and that's how the textbook approaches it. They teach everything about substitution first, and then they introduce elimination later, and then they backtrack and say, well, can we predict any of these are elimination reactions also? Don't worry about that. Okay? If you need more practice, definitely practice the mechanisms. You can draw the mechanisms for each of these three examples. Should we try some more? Let's try D. Same deal. I'm going to give you the problem, and then I'm going to ask you to pause the video. D. Let me find my example. Ooh, this one's an interesting one. I like this one. Okay. Very interesting, especially if you are good with naming molecules. You'll see something a little bit unusual here. This is acetic acid. But I think the textbook puts it underneath the arrow to emphasize also that there's no other solvent, there's no other liquid. So the solvent is also the nucleophile. You're going to have to decide which atom on the nucleophile is going to do the attacking. Try your best, okay? Definitely have your notes, definitely have your textbook. See if you can figure this out, if you had any resource that you want, and then with practice, you could start doing these problems without any of those extra resources. Pause the video and then come back in about 3 to 6 minutes. Put something on your paper, okay? When I come back and we go over the answer, mark anything that you got wrong with a red pen X. Okay, don't erase it, don't black it out. We want to see your mistakes. You want to see your natural tendencies. That way you could recognize them if they're about to happen on the actual exam. Okay, go ahead and pause the video. Alright, obviously this is your alkyl halide. It's secondary, but what do you notice? If I have this carbon here, that's allylic. So the halide is called a secondary allylic alkyl halide. These two are the same. Okay, they're the solvent and the nucleophile. The solvent, well, they're the same. Acetic acid is polar and it's protic. That hydrogen is pretty acidic. It's a carboxylic acid. So it's protic. I'm going to put it here already, SN1. I don't know if this is SN1 or SN2, just from the secondary, but since it's secondary allylic, we know that's a very stable carbocation. We're going to say it's SN1 because you go through a stable carbocation. Even though it's secondary, but it's secondary and allylic. That adds to the stability. The nucleophile. The nucleophile is a little bit tricky. You have to decide what oxygen is going to be the attacker. If this top oxygen attacks, then that oxygen would be permanently positive because we can't remove any bonds. But if this oxygen attacks, it will initially be a positive, but we could remove this hydrogen to make it back into neutral. Not neutral here, neutral in the product. Okay. The other thing, we know it's neutral. What do we say? How does that affect the nucleophilicity? neutral molecules are typically poor nucleophiles. That tells me SN1. Alright, I'm gonna, before I forget, on an exam, SN1. Okay, SN1. Product. SN1 means scrambling. Do you see that? Scrambling. So even though this is chiral, carbon, we're going to get both R and S in our final product. The hard part is, can you draw the product based on all of this information? You have to practice. Even with all of this information, this might be difficult because, look at my product. I'm going to draw the dash first. Because this oxygen's the attacker, you have an oxygen there, and the rest of the molecule. There used to be a hydrogen here. There used to be this hydrogen, but that would make the oxygen positive. So in the mechanism, the last step in the mechanism is to remove that hydrogen. Understood? Because it's SN1 and the carbocation is flat, you get a mixture, racemic mixture. We have this. Okay? Why do we get that? Let me show you, not the full mechanism. Let me just circle first the answer. Okay, that is the answer. Right? That, to me, represents something that can separate the A's from the B's. Alright? Let me show you the intermediate. Because A, I want to show you the flat carbocation, but also I want to show you how the attack happens. Okay. Actually, I might just draw out the full mechanism. Forget about that. Okay, I'm drawing you the mechanism. Okay. See, there is stereochemistry at the beginning. But remember, the orange cat is just going to wait because it's a poor nucleophile. It's going to wait until the black cat leaves. What do I get? See, there's a hydrogen there, right? I'll draw the hydrogen, but I'm going to draw it flat because this is a trigonoplanar carbocation, right? Trigonoplanar. And I like to draw, and I ask my students to draw every molecule that is produced in the preceding step. Okay, so we did kick out a bromine. In this case, a bromide. What is this nucleophile doing? Okay, some of you are probably a little bit confused. What do you mean? Well, how do I know which oxygen to use to attack? I'm going to use this oxygen here, and I'll explain why in just a bit. Going from right to left. Oh, and there. We don't have to kick out anything, right? This carbon needs a fourth bond anyway. I'm not going to show stereochemistry. We already know that this is flat. So you know you're going to get a mixture of front and back. Okay. So I'm not going to draw wedges and dashes. I'm just going to draw a line. This is what I have. See, that H is still there. That H is still there. That's why you can't use this oxygen to attack, because if I use this oxygen, that oxygen will become positive, but there's no hydrogen to remove to get it back to be neutral. Here we can. And I'm going to use, I think I've done this in the previous videos, use the halide as the thing that deprotonates a charged product. Now my product is uncharged, and that is the product without any stereochemistry. Okay. We did produce HBr. Okay. I typically do take off points because I do want you to know what is produced at each step. But our main product is this, right? And we have that up here. 4 examples. Do all your notes in green, do your answers in blue, indicate the type of mechanism, and if you need extra practice, draw the mechanism for each of those 4 reactions.